Hello and welcome to the Unit 8 Section 2 video on key features of quadratics from a graph. So we are going to, in this section, be taking a look at graphs of quadratics, and we're going to determine some of the key features. Okay, what kind of information can we pull off of these graphs that tell us a little bit about our quadratic? So recall that a quadratic function is a function that can be described as an equation of the form ax squared plus bx plus c, where a is not 0, because if a is 0, we don't have a quadratic function. The highest exponent of a quadratic equation is 2. The graph of a quadratic function takes the shape of a parabola. And of course, this form that I presented here for you is standard form. Okay? Of course, you also have vertex and intercept, but here we have it in standard form. Well, now, let's talk about some of the parts of a graph. Okay? So, here's a look at a parabola to the right here. And we've got several things. So we're going to match the definition to what we're looking at on the graph. So our first definition is a line that passes through the graph in such a way that each side is a mirror reflection of the other. Well, that line right here is your axis of symmetry. Your axis of symmetry divides us into the right and left side of your graph. And if you were to fold along the axis of symmetry, your graph would fold on top of itself. Now, the points or point where the graph crosses the x-axis, well, here it is here. Here's one, here's another. Those are obviously our x-intercepts. But we do have more than one word for x-intercepts. And so get familiar with this vocabulary a little bit, because you're going to hear x-intercepts, especially in quadratics, be referred to as not only x-intercepts, but also as zeros or roots. Okay? So anytime you're being asked for the zeros, you're being asked for the x-intercepts. Anytime you're being asked for the roots, you're being asked for the x-intercepts. And when you solve a quadratic equation, eventually you're going to get into that. You're solving for the x-intercepts. That's what you're looking for when you solve a quadratic equation, when you solve for x. Now, the point where the graph crosses the y-axis, well, here it is at this point. This is our y-intercept. And then our highest or lowest point on our graph, depending on how our graph is oriented, that's going to be our vertex. Now, as previously shown, some parabolas open upward and some open downward. Notice that the only difference between the two equations is the value of a. When a quadratic is written in the form y equals ax squared plus bx plus c, the value of a determines the direction the parabola opens. If a parabola opens upward, the vertex is the lowest point. If a parabola opens downward, the vertex is the highest point. So let's make some of those comparisons here. So if we are concave up, our parabola is oriented upward, the value of a is going to be positive. And that means our parabola opens upward, and our vertex value, or our y value, is going to be a minimum. If we are concave down, then we have a negative value of a. Our parabola opens downward, and our vertex is going to be a maximum. Now, there are some other features of quadratics that we do need to discuss. Okay, so bear with me here. There is a lot of wording here, but I'm going to mainly describe these things using the graph on the right here. So let's look at this first graph on the right. The domain of a function is the set of all possible x values. Okay, so your domain, you're going to be looking left to right, and you're going to be looking at all the possible x values we have. Unless a specific domain is given, you may assume that the domain of a quadratic function is all real numbers. So if you have an arrow on the left, that means we're coming from negative infinity, because like on the x-axis, we have an arrow on the left, so that means we're coming from negative infinity. The arrow on the right indicates we're going to positive infinity. Now, the range of a function is the set of all possible y values. The range will be determined by the maximum or the minimum. Remember, the range is the only interval feature that uses y values. So this is the only thing where you're going to use y values for. Everything else will involve x's. So our range here, we start from -4. So we start from bottom and go our way to the top. So we start from -4 and we include it. So we use a bracket. And it goes to infinity, which is indicated by our arrows on the top. So our range is -4 to infinity. Now, end behavior describes what is happening to the function as x approaches the positive and negative infinity. For the graph on the right here, as x approaches infinity, so x being infinity is on the right side, our arrow is pointed upward. So f of x, which is another way of saying y, is also going to infinity because we're pointing up. As x goes to negative infinity, so now we're going to look at the left, f of x goes to infinity on this side as well because, again, our arrow is pointing upward. Now we have increasing intervals and decreasing intervals. An increasing interval is a set of x values when the function is going up. Decreasing interval is the set of x values when the function is going down. So again, you're going to use x's here. Literally, this is where our graph is decreasing. This is where it's literally going down. And it goes down until we get to x equals 0, okay? So we got decreasing from negative infinity to 0. Then we're increasing from 0 to infinity. X equals 0 to infinity, indicated by the arrow on the right. A positive interval is the set of x values with corresponding positive y values. Okay? So, in other words, a positive interval is where the graph is above the x-axis. A negative interval is a set of x values with corresponding negative y values. So, in other words, negative interval is where the graph is below the x-axis. So, here on this graph, we are positive from negative infinity to -2, negative from -2 to +2, and then we're positive again from 2 to infinity. Since we have two positive intervals, we are going to union the two intervals together with a little u in between. So you're going to write the first one, you'll write the second one, and then you'll put it together as one answer by putting a u in between. Now that we have covered all the different key features that we need to be able to pick out of a graph just visually, let's do an example. So here we're going to determine the key features of this graph parabola. Starting with the direction. Since both arrows are pointed up, we are concave up. The vertex, we're going to get the ordered pair of where the vertex is. So the vertex is located here, where I put the crosshair. So the ordered pair is going to be 1, -4. The axis of symmetry is this x value, where we can draw a vertical line. So x equals -1, or I should say +1. Okay, that should be a +1. For our min or max, our min is what we have, and the value is at y equals -4. We have a y-intercept at 0, -3. Our zeros, remember, zeros are a term for x-intercepts, are at -1, 0 and at 3, 0. Our domain, we've got an arrow on the left and an arrow on the right, so that means we go from negative infinity to positive infinity. Our range, we start from -4 and work our way to positive infinity. Increasing and decreasing, I'm going to work together. Okay, so let's start from the left. We're decreasing first, so we're decreasing from negative infinity to 1. And then we start increasing from 1 to infinity. Our positive interval and negative interval, I'm going to work together. So we start out positive from negative infinity to -1. And then we become negative from -1 to 3. And then we're positive again from 3 to infinity. Okay, so I kind of work increasing and decreasing together, positive and negative together. For our end behavior, we have As x approaches infinity, so we're looking at the right side, since our arrow is pointing up, f of x goes to infinity. As x goes to negative infinity, so now we're looking at the left, our arrow is pointed up, so f of x also goes to infinity in that direction. Let's check example 2. So our direction is concave down this time. Our vertex is at 2, 1. Our axis of symmetry is along that x value of our vertex, so x equals 2. We have a maximum, and that maximum is at y equals 1, which happens to be the y value of our vertex. Our y-intercept is at 0, negative 3. Our zeros, or our x-intercepts, are at 1 and 3, so 1, 0, and 3, 0. Our domain, arrow on the left and the right, tell us negative infinity to positive infinity. Our range, going from bottom to top, we start from negative infinity and go to 1. And then increasing and decreasing. We start off increasing from negative infinity to 2, and then we decrease from 2 to infinity. Our positive and negative intervals, we start off negative from negative infinity to 1, and then we're positive from 1 to 3, and then we're negative again from 3 to infinity. As x approaches infinity, so we're on the right side, f of x is pointed down, so we're going to negative infinity. As x goes to negative infinity, so we're on the left, f of x, again pointed down, we go to negative infinity. Let's talk about one last key feature, and that is the average rate of change. So the rate of change is a ratio that compares the amount of change along the y-axis and the amount of change along the x-axis. When you did this in a linear function, you refer to this as slope. It's your rise over run. But since we're not working with a linear function anymore, we're not talking about slope. We're just talking about the rate of change, or the average rate of change. On average, how much does your graph change from one point to another along the graph? So you're going to use the same formula that you're already familiar with. You remember this as your slope formula, y2 minus y1 over x2 minus x1. You're going to use this formula to do the average rate of change as well. So we're going to start with how to do it if you have an equation, okay? First, you're going to substitute the first x value into the equation, solve to get y. This will be your first point. Then you're going to substitute the second x value into the equation, solve to get y, and that'll be your second point. Then you're going to plug both of the points into the average rate of change formula and simplify. So let's see how this works in an example. So for A, we are given that equation, and you're given the interval 1 to 3. That 1 to 3 is your x1 and your x2. So we're going to take our x1, our first x value, we're going to plug it into the equation. So everywhere there's an x, you're going to put a 1. And then you're going to evaluate it. 1 squared is 1. 2 times 1 is 2. 2 plus 5 gives us 7. So the y1 that goes with our x1 is 7. Or in other words, we have the ordered pair 1, 7. We're also going to do this for the other x value. So we're going to plug in 3. 3 squared is 9. 2 times 9 is 18. 18 plus 5 gives us 23. So now we have our x1, y1, which is 1, 7, and our x2, y2, which is 3, 23. Finally, we're going to take our average rate of change formula, y2 minus y1 over x2 minus x1, and you're going to plug in each of these values. Then you're going to do the math on the top. 23 minus 7 is 16. On the bottom, 3 minus 1 is 2. And 16 divided by 2 is 8. So our average rate of change from 1 to 3 for that function is 8. For B, same sort of a deal, okay? We're going to plug in negative 1 for our x first. Negative 1 plus 1 gives us 0. 0 squared is 0. For the second point, 2, we're going to put in 2 for x. 2 plus 1 is 3. 3 squared is 9. So x1, y1 is negative 1, 0. x2, y2 is 2, 9. Then you're going to plug those into your average rate of change formula. 9 minus 0 gives you 9. 2 minus negative 1, which is 2 plus 1, gives you 3. 9 divided by 3 is 3. Now let's talk about average rate of change from a graph. What you're going to do is take your x values and you're going to follow your x value up to or down to your graph, depending on if your graph is above or below at that x value. And then you're going to find the y that goes with it. And then you'll plug in your points into your average rate of change formula. So in example 4, we have our x's given to us. 1 and 4 are x1 and x2. We're going to find x equals 1, so here it is on my crosshair. And we're going to follow that down to my graph. And then I'm going to follow my graph back to my y value. So the y that goes with my x is negative 6. So with 1, we have negative 6. Now we need to find the y that goes with 4. So we follow over to 4, and we're going to follow this up to our graph. And then we're going to follow this back to our y value, which is 3. From here, we just plug it in. 3 plus 6 is 9. 4 minus 1 is 3, so our average rate of change is 3. So there is less work involved when you're presented the graph, because you just have to find the y off the graph. For b, 3 and 6 are our x values, so we'll go ahead and put those in. So we're going to follow over to 3, follow up to our graph, and our y value is 1. For 6, we're going to go over to 6, follow that down to our graph, and back to our y value, which is negative 2. Plug those into our average rate of change. Negative 2 minus 1 is negative 3. 6 minus 3 is 3. And you've got negative 1. All right, the last place where you're going to be looking for average rate of change is going to be from a table. This is the easiest of all. You're given your two x values as normal. All you have to do is read off the table what y's go with it. So here are my two x values. With 1, we have 5. What goes with 3? Negative 3. Plug those in and evaluate. Negative 4 is what we get for A. For B, these are my x's. With negative 3 goes 23. With 0, we have 8. Plug those in and evaluate. And you get negative 5 for your average rate of change for that last example. All right, so that wraps up this section of Unit 8. We've looked at a lot of key features, and we've also looked at how to do average rate of change. Coming up in the next section, we're going to talk about how you go about graphing quadratics. How do you create a graph by hand? And we're also going to talk a little bit about how to evaluate problems in real-world situations.